Whenever you're done. If you multiply 1/5 0 by a column, well, the 0 is going to match up with the second number. All you're going to be doing is multiplying the 1/5 by the first number, right? And that's going to give you 1.8.6. Okay? And then second row, well, you got to do a little arithmetic there. Negative 2/5 of 5 is -1, right? Negative 2, I'm sorry. And you add that to 1 times 2, which is 2, you get 0. And then negative 2/5 of 4 is negative 8/5. Add that to 1 times 7, which is 7. And you do the arithmetic, 35/5, negative 8/5 gives you 27/5, which is 5.4. Okay? Since I did it in decimals. Okay, and the last is going to come out negative 5.2 because you all say it will. Okay? Fair enough? Oh, well. Looks like it works.
Yeah.
Okay, well, the big advantage of this, okay, we're going to call this matrix E1. We're going to call this matrix E2 for elementary matrix 1, elementary matrix 2. To complete the reduction all the way down to the, complete reduction, you're going to need an E3 and an E4, right? So we can say that you're going to get 4 matrices, one for each of the row operations, divide by 5.4, then add negative 0.8 times this row to this row, and the arithmetic gets nasty. Okay? Probably easier to just multiply your elementary matrices out to do all the arithmetic, but maybe not. But the use of elementary matrices goes way beyond that. And I'll give you some flavor of it. That's going to equal 1, 0, 0, 1 times a couple of numbers over here that we don't know right now. Okay? And it's easy to see what E3 would be. It's just going to be 1, 0, 0, 1 over 5.4. Or 5 over 27, if you want to use the fractions, which I kind of recommend, okay? And then E4, well, you're going to get a 1 here. It's just going to be 0.8 times this added to this, right? That's going to give you the matrix. 0.8 times this added to this gives you a 0.8 here, 1.801, right? So I can tell you what E3 and E4 are if I know what the steps are going to be, okay? So there might be places where it's advantageous to do that. Although, if you try to do too many steps in too big of a matrix, you're going to start losing track of your numbers. You're not going to know what numbers go. So you're probably not going to do it that way. Still, you see that you could. So we have this product, okay? Well, I'm going to claim that tells you that if I was to multiply this on the left by E4 inverse, E4 inverse times E4 is the identity. That's what an inverse matrix is. E4 then goes away. No longer there. The E4 and the E4 inverse are gone, and now I've got an E3 inverse facing E3. which goes away, leaving me an E2 inverse facing E2, which goes away, which leaves me an E1 verse, E1 inverse, E1, which also goes away. Okay? Leaving me this. Okay? It's really easy to inverse a matrix, an elementary matrix. You just go backwards. Okay? You multiply the first row by 1/5, right? The inverse of this matrix, multiply the first row by 5. Okay? We did -2 times the first row added to the second, right? Okay? What do we do to get back? We add 2 times the first to the second. Okay? So which is going to be the same as this, but a +2 here. Okay? I think I said that right. If you switch 2 rows, you just switch the same 2 rows and you're back where you started. Okay? So it's really easy to write down the inverse elementary matrices. And what this does is it gives you, you can use this, and you don't even go all this way. Actually, you only go this far, and you get what's called an LU decomposition of your matrix. Okay? Which is very convenient for solving matrices. Being the first example of the decomposition. You don't have to understand that. I'm just previewing it. We'll talk about it next time. Okay? Because I will be assigning it over the weekend. So I wanted to get your feet wet with elementary matrices, which is really pretty much the last topic in Chapter 2. So you already see what they are. We'll talk more about their properties. Okay? Check out the assignments page. It'll probably be later.